you very much for coming here this afternoon to the GlobeShow, to the Hadron Cafe. Thank you very much for visiting CERN. I hope you've had a great day. Now we're going to spend half an hour. Stay with us, please. We're going to talk about the medical applications of particle physics. You've seen a lot of interesting things around the site, but here it's medical applications. We have a guest speaker, Manjit Dosanjh, who is a biologist. You don't meet too many biologists at CERN. Manjit, why do we have a biologist at CERN?
Interesting that you asked me that, Mick, because a lot of physicists ask me the same question. I'm here to look at applications and technologies which can be extended into the health arena. And modern medical physics actually started in 1895 when X-rays were discovered. And soon after, in 1898, radium was discovered. And from then on, medical physics has really taken its main play in the field. And I think it's interesting that you call this Hadron Cafe, because one of the things I want to tell you a little bit about, which is a new area, is hadron therapy.
Okay, so what is hadron therapy?
Okay, hadron therapy is actually using particles for treating cancer. Up till now, there are about 2 million people every year diagnosed with cancer in Europe. And the main tool for curing cancer, that's about 40% of the total cure, is by radiation therapy, which is using X-rays.
So why would we want to replace X-rays with something like hadron therapy?
Okay, and the reason for that is, although X-rays are effective in curing, however, due to their physical profile, they deposit most of the energy near the surface, near the entrance. So if you are trying to treat a tumor which is further in or is near to a critical organ, what happens is that you deposit a lot of energy in places where you would not like to have.
So in fact, when we use X-rays, we also kill healthy tissue. Maybe we should say, what is a hadron?
Hadron is, it's a charge. In this context, okay, well, besides being quarks, but in our case, we are really looking at protons and carbon ions. We could also use particles in between, but from the initial studies that have done so far, protons and carbons have been selected because protons have the same energy as X-rays. However, they're able to deposit the energy in a very precise way. So you can actually deposit it exactly where the tumor is without damaging the healthy tissues nearby. And we are using carbon, which has the same property as protons, but is able to deposit 24 times as much energy. So it's much more effective at killing the cells.
We accelerate protons in an accelerator and we fire them at a tumor. But how come, what happens then? So the protons pass through the body and they only deposit the energy at the tumor, is that right?
Okay, the reason is because protons are quite large compared to what the matter they're passing through, which is mostly electrons. So they deposit their energy at one point called a Bragg peak. So most of the energy is deposited exactly where you wanted to have it deposited. So if you want it further in, you can accelerate them faster. If you want them slightly further towards the surface, you accelerate them a little bit less. So you can deposit them exactly where you want.
Okay, so that's one medical application of the type of physics that we do at CERN, trying to more effectively kill cancer cells. Mm-hmm. Are there others?
Okay, so actually to be able to kill cancer cells, you need to know where the cancer is. So one of the other fields which we are looking at is detectors. Using the detectors we are already using in our Atlas, CMS, and other experiments, how can we use the same detecting devices to detect more precisely the tumor? Because if you can detect it more precisely and very early, the chance of curing the cancer is much higher. And also, as I've just told you, since with hadrons you can deposit the energy much more precisely, it's only really, really useful if you can also know exactly where to deposit it.
So, some of the techniques that we use in particle physics at CERN are also used to isolate or detect where tumors might be.
That's right, yes. And one of the main imaging devices that is gaining a lot of importance right now is positron emission tomography, or PET. And the reason why it's really taking off is that it's one of the few detection imaging devices which tells us something about the state of the cells and the tissues. Most of the other imaging methods is a passive method of where things are, but the PET actually tells you whether the cell is acting normally, or there's a defective activity, or it's growing rapidly. For example, in cancer cells, which divide very, very rapidly, they use a huge amount of glucose. So if you can label the glucose with a tag, which is like a magic marker, and then you can detect it, you can see exactly where those areas are. And so that's one of the things we use.
Okay, so we find out where the tumors are. We kill them with the proton beams or possibly ion beams. Are there other applications of particle physics?
Okay, there are a number of activities, but one of the things, for example, is in most of the detection, as we talked about positron emission tomography, but you can make compounds in which you put a very exotic or a specific radioisotope so that you localize the area where you want it in the body. With this new technologies of human genome being sequenced, you can have very specific targeted proteins. And if you can tag a radioactive isotope, you can localize both for treatment, because it's like putting granules, if you like, in the brachytherapy, but here you actually have a tag with a protein, or for detection. So we also, not only did we long time ago make isotopes, for example, in the Geneva Hospital, who were collaborating with us for looking at their tumors, now they have their own cyclotron for making this labeled glucose I talked about. However, if people are looking for new advances and new exotic isotopes which they cannot make readily at home, we can help to do that.
Okay, thank you, Manjit. We're going to take a brief pause from medical physics here. We're going to go over to the stand over there where we have a couple of young people, a couple of young physicists, physics students have come all the way from Zagreb in Croatia, and they're going to show us some interesting experiments. Physica Express.
Hello, this is Ivan and my name is Iva, and we're going to show you a few of our experiments. First of all, we are going to show you how our vacuum bazooka works. So this is projectile. It's a cork, and the reason is why it's named bazooka is because it will launch that projectile somewhere over there. So
hopefully not in my direction, please.
No, we're aiming at the audience more than you. No. So what we're going to do, we have this pipe and we're going to make vacuum inside it. And first we have to seal both ends. With one end is sealed with this cardboard and the other with
If you look at the screen, you'll get a better view.
Okay. We're going to turn on our vacuum pump and create vacuum inside this tube. Okay. And wait for a little while. Now, atmospheric pressure is greater than the pressure inside that tube. So what he's going to do is going to push that cork into the tube, accelerate it, and out to another end. Now it's going to... Okay.
Good, we didn't kill anybody this time. Great.
Hopefully
another experiment.
Okay. Another experiment we're going to do is it also is related to pressure. And it's called Cartesian diver. And the reason it's called that way is because we have this glass tube, which is open on one side and closed on the other. And half of it is filled with water and another half with air. And now it's floating on the surface of this bottle. Now if you can zoom into that and watch it on that screen. So now it's floating. And if we... okay, you can see that, okay. And if we press the bottle, that little tube will fall down. And why is that? Well, we're compressing this bottle of water, and you really can't compress water. So what it happens is that this little box of air is being compressed, and it becomes more dense. And things that are more dense than water will not float, it will sink down. So, and we release the pressure, it comes back again.
Is this something we can try at home?
Yes, of course.
Okay.
It's not really dangerous at all.
Have you got one more? Quick one?
One more, okay. We have here liquid nitrogen, which is basically you cool air to minus 200 degrees Celsius. So it's really cool. But we can put in our hand and nothing will happen. But if we put the leaf in and keep it for a couple of seconds, and we take it out, and it becomes like glass. What happens, that liquid nitrogen, it cools the water inside that leaf and makes crystals of it. So when you take out, it's hard and acts like glass or like a piece of ice. So we can break it.
Okay, thank you very much, Physica Express. We're going to listen to the band now. While you're listening to the band, think of some questions that you might want to ask Manjit during the next question and answer session, okay? Dazzled.
Listen to me while I'm talking to myself. I won't be long and I'll make it very clear. It's a relief that you're not around to hear about a love that gathers dust upon the shelf, dust upon the shelf.
thank you to Dazzled. All of the bands that have been playing here today, just to prove that scientists have other lives. They are all working physicists, engineers, technical people at CERN. So scientists do have lives outside of science. Now it's up to you. Do you have any questions you'd like to ask about the medical applications of particle physics? Please don't be frightened of asking the questions. Vous pouvez aussi poser les questions en français, bien sûr. Somebody at the back there.
Thank you. I was curious as to how long the hadron radiation therapy, or hadron, pardon me, has been going, and what kind of success rate you've had in real applications.
Okay, in terms of within Europe, in GSI in Germany, they used actually a physics laboratory to treat around 300 patients, and the success rate was it was so successful actually that the German government backed a facility which will be starting to treat patients in Heidelberg in the next couple of months in a clinical setting. And then the second facility to be opening, again hospital-based in Europe, will be in Pavia near Milan. And within our network, we have a European network of light-ion therapy called ENLIGHT. From 17 countries, there are 5 or 6 other facilities approved, and 2 which will be actually treating patients in a clinical setting.
Okay, thank you. Another question?
I prefer speaking in French because my
oui,
English is not very well. I want to know.
En français, si vous voulez.
J'aimerais savoir de quel est-ce que l'appareil que vous parlez là, est-ce qu'il sera commercialisé dans les hôpitaux dans le monde? Est-ce qu'il va être comme un scanner ou quelque chose comme ça?
We're talking about hadron therapy itself?
Yeah.
Okay, the hadron therapy machine, for proton therapy, there is a company in Belgium called IBA, and there are a few others, which does proton therapy machines commercially. For the carbon treatment, which is much more effective because of the more energy and the fact that it's able to treat tumors which are radio-resistant and using old protons and X-rays, there is Siemens is the one that is backing the facility in Heidelberg. Of course, there are other companies that would like to try to also do the same way, yes.
Okay, thank you. I've got a question. I've heard that we had a talk this afternoon about the grid. I understand that the grid may also have an application in medical physics, yes?
Yes, well, grid, I think what's clear, of course, we are doing grid at CERN for our particle physics and the large amount of data and sharing information. But you can imagine now with the medical data and the medical information and medical technologies becoming more and more specialized, you can't just go to one doctor or one type of imaging to be able to have a diagnosis. So the idea behind being able to get a number of, say, for example, imaging technologies from X-rays to PET, being taken, then the image coming to a central point, and then also the diagnostics, and then the person who's going to give you an opinion, a consultant if you like, he or she may not be at the same places where the image is happening. So it's clear that if you can use the grid also for connecting and sharing resources, not just the imaging resources, but also the consultation you can get, that you can use something in a similar way to the grid. But for our perspective, from the health perspective, what's even more important is that early diagnosis and screening is becoming the thing that we should really do for prevention. Now, if you want to start taking mammograms, for example, for screening breast cancer or prostate scans, and you want to compare them and store them, then an idea of grids where you store images every year and then you can compare and then also get second opinions, or if the patient moves and they go somewhere else, then of course that's obvious where that's going. And on top of that, if we talk about hadron therapy, there are only 2 facilities at the moment which will come online, Italy and Germany. If you want to refer patients to these places, I think the idea of sending a sick patient to this place to be tested to see if they are suitable, rather, you know, if you can find alternative methods of trying to use this idea of grid and patient referral remotely using this, it's clear that these are assets one can use for the next generation.
One last question from the audience. Yes. Let me give you my microphone.
Thank you. About what you talked, I know. Yes? Oh, okay. It's Mobi Health. center. It's not in use, I think, now. But do you think all people in the world is going to use this machine, or
you mean
only the people who can pay it?
You mean the hadron therapy?
Yeah.
Okay, one thing is not everybody can use the machine because there are only 2 machines and you can only treat a few patients. This is clear. Okay, so that's one. So therefore, these machines should be used for patients which cannot be treated any other way. That's clear. The second thing is, the idea is not only the people who can afford to use these machines, because actually the cost of treating with hadron therapy versus X-rays is not that different. The cost comes from the development that's taken place into getting to these machines and then actually building the machine and installing it. So the machines are very expensive, but the treatment itself, the cost is not that different. And then also when you're delivering the energy much more precisely, the secondary effects are much less. So in the end, the cost to the health services is actually going to be more effective. And for the patient and the quality life, since you can deliver energy much more precisely, rather than the X-ray, which you normally have treatment for 6 weeks, you can actually give this energy in fewer fractions. So for, in Japan, for example, some of the stuff is being done in 5 times or 1 day. So actually, if you're talking about only people who can afford it, the cost of treatment is not that different.
Okay, I think we have to stop there, but I think the answer basically is that all these things are in their infancy. We're just beginning to learn how to do this, but come back, and I'm sure that there will be many centres in the world. So thank you very much for coming this afternoon. Thank you to our band. Thank you to our young people from Zagreb. Big thanks to the technical team. Would you like to stand up now and leave by this door? And I hope that you have a fantastic evening and that you've enjoyed your day at CERN. Thank you.